Good day, everyone. We're from Group 1 and we're going to present our mechanical design process progress on portable and decentralized off-grid solar wind hybrid system. And as for the first step in this SIGLI mechanical engineering design, we did the identification of needs, where we start this by recognizing that in Indonesia, particularly in remote regions such as Papua or other treaties areas, namely frontier, outermost, and disadvantaged areas, they still face challenges in achieving reliable electricity access. This may be due to the geographical isolation or the limited transmission infrastructure. But on the other hand, we know that if we extend the centralized grid system, it's gonna be economically inefficient, and as a result, we need a decentralized and independent energy system that can operate locally, so we don't rely on large-scale infrastructure. And also, since we have like a very strong renewable energy potential, for example, like we have really high solar irradiation by 4.8 kilowatt hour per meter square per day, and we also have adequate wind speeds averaging around 5.52 meter per second. So this makes using solar and wind energy very suitable for remote electrification. But there are challenges when using this renewable energy. For example, we have like really high upfront costs, and because the source of this energy is intermittent, so we require energy storage. And there are also some concerns like environmentally and socially, for example, because of the typical land use and the visual impact.
After identifying the needs, we translate those needs into specific engineering requirements. First, let us discuss for the main specifications. For functionality, our system is designed as a compact and modular small-scale unit. The blade length is less than 30 centimeters, and the total height is less than 70 centimeters. This compact size ensures that the system can be easily transported and installed in remote villages without heavy machinery. We also target a cut-in speed of around 2.5 meters per second, so it can start operating even in low wind conditions. For load requirements, the blade mass is approximately 3 kilograms, and the total mass is kept below 10 kilograms. Limiting the mass reduces centrifugal force and structural stress during rotation. The system is designed to withstand wind speed up to 30 meters per second based on IEC 614002 small-scale wind turbine class 4. This ensures durability under operational and gust wind conditions. For safety, we require at least one automatic overspeed protection mechanism. This is essential to maintain structural stability during strong wind or sudden gusts. The goal is to prevent overspeed damage, structural collapse, and potential hazards to nearby users.
So the secondary specification, where we focus on the performance, where the minimum energy storage capacity needs to be 3 kilowatt hour per day. This ensures sufficient daily electricity supply for the essential rural needs such as lighting, communication, and small appliances such as toaster or some fan or lamps. And second is manufacturability, where they use outsets of recycled plastic for the structural components of the wind turbine, which reduces the production costs, supports sustainability goals, and allows easier forming and fabrication process of the wind turbine. As for the tertiary specification, first in the environmental, where the turbine shall minimize environmental impact through the use of recycled materials and low noise operation. The low noise operation needs to be as low or lower than 45 decibels. This reduces material waste, limits ecological disturbance, and supports environmentally responsible rural electrification with the recycled materials. And the second is the social, where the turbine shall include a mechanical visual safety indicator to signal a higher wind speed or overspeed conditions. This not only helps the wind turbine to protect itself, and this also helps the village community or the village people to provide a visual warning to the users without requiring any electronic sensors. And at storm events, this could be really useful for the villagers.
Alright, having defined our specifications, now we can try to create a concept. So at this stage of synthesis, we have one of the concepts being a foldable H-rotor vertical axis wind turbine, and it uses an umbrella-like mechanism that allows it to be foldable and hence portable. And so, the umbrella mechanism is meant to be used not only for the portability but also as a protective mechanism, where if the wind speed exceeds the limit mentioned previously, then the frame will close and the blades will be collapsed, and it reduces wind exposure. Right, as you can see here, this is what our initial design looks like. And so in normal condition, the blade will rotate normally, just like any other H-rotor wind turbine. But when it's folded, it can be folded when there's like a fast wind speed by using a linear actuator to control the movement.
The second concept is the Darius Savonius hybrid vertical axis wind turbines. This concept combines two types of wind vertical turbines, where the first is Savonius rotor and the Darius rotor. Savonius rotor works really well at low wind speed, but the catch is that in general it gives less energy output, with a wind coefficient where a research states that the wind coefficient is 0.1. Compared to the Darius rotor, which is more efficient at higher wind speed, and the same research also states that the wind coefficient is exactly 0.3 at higher speed, but the blade has trouble at lower wind speed, and it doesn't self-start well due to the blade shape making the torque zero or almost close to zero at lower wind speed. So at 6 or 7 meter per second wind speed, or below 10 meter per second wind speed, the coefficient is calculated to be close to zero, if not exactly zero. And the same research also calculated the coefficient at the higher wind speed, which is calculated to be 20 meter per second to 30 meter per second. The wind coefficient is calculated approximately 0.3 at average. By combining them, the turbine can operate under a wider range of wind conditions, maybe at lower or higher wind speed. So the way that this turbine works is it has one shaft which is connected to two blades. As you can see here in the picture, the straight blade is the Helix Darius blade, and the curved blade is the Savonius blade, where the Savonius will go and rotate at lower wind speed, and then once the wind speed gets higher and higher and higher, the Darius blade comes in as the a better addition at the higher wind speed because by its higher wind coefficient, which helps the generator generate more power output and more consistent at each varied wind conditions. And since the both rotors share the same shaft that is connected to the gearbox or it's directly to the generator, this will make the generator generate the power from the same shaft with no matter the blades here.
So for the third concept is modular horizontal axis wind turbine with integrated charge controller. So concept 3 is a portable compact wind energy generator designed to capture wind energy and convert it into electrical power in a mobile format. Unlike traditional large-scale wind turbines, the wind turbine is scaled down to a size that can be carried in a backpack and deployed quickly in outdoor or off-grid environments. The main functionality is where the rotational motion drives a generator integrated within the device, producing electrical energy directly from wind energy. The generated electricity is managed through an internal charge controller that stabilizes voltage and prevents electrical overloads, and then it is stored in a battery bank. This allows the system to provide a continuous power supply even when instantaneous wind conditions vary or when the wind temporarily stops. Because of its lightweight, foldable design, setup can typically be completed in minutes, and the turbine can be mounted on a simple support stand for elevated wind access. This makes the system suitable for a range of applications, including off-grid living, disaster backup power, and others. Here are some references for our presentation. That's all from Group 1. Thank you.